Since 1960, this very strong upward trend. But you also see a lot of variability. This is the annual variability, the annual weather variability that we're talking about. And last year was cool, but if you look at it and with respect to the rest of the cooler periods, it still follows that trend. So you can see, even in a global warming scenario like we have and we are experiencing here in Ohio, you still have variable weather that contributes to that annual mean temperature. Pulling back further, and you've seen this graph already, looking at the global mean, global land ocean temperature index, which is the black is the yearly annual mean, and the red is the 5-year running mean. And just this unprecedented rise in temperature here over the last 30 years. And there's been a lot of attention about this quote-unquote recent pause, and Ellen also brought up the fact that a lot of the climate scientists, and myself included, are in the it comes down to the global ocean heat content. Okay, so we're not seeing necessarily a slowdown in the heat that's being retained by our Earth system here. It's just being retained much more so. We're actually seeing evidence from this that is being stored in the ocean. So the whole climate system as a whole is still increasing in terms of heat retention. All right, so that's the differences between weather and climate from the perspective of Ohio and then out to the global. So how do we model these two areas? And they're modeled very differently, and one of the things that I want to talk about is really the difference between modeling these two types. The numerical weather prediction, okay, we're going to start out by collecting a ton of observations. All right, so this was, I pulled this yesterday. This was the surface obs yesterday. So we're collecting a ton of stations. In the United States is actually, we're lucky. We're just inundated with tons of data, okay? So we collect surface observations. We collect radar observations, and then we're collecting satellite observations of what's happening. We're sending weather balloons up in the air, the radiosondes. We're collecting all this information. We're creating upper level charts. So what does the weather look like in the upper levels of the atmosphere? And then we assess the present climate. We assess the present state of the weather, the atmosphere. We call this an analysis. And then this analysis then is used. This is analysis yesterday, that was valid yesterday, 1500 UTC, of low pressure, high pressure regions and pressure, cold fronts and warm fronts across the country here. All of this information is then fed into a computer model, and then based on mathematical and scientific relationships, it's integrated forward in time to predict the changes that we're going to incur. And the important thing is to interpret the results that happen. So this was a 24-hour forecast, okay, that was valid this morning, based on the initial conditions that we saw yesterday. And what this is an expected result, prediction about what's going to happen based on the current state of the atmosphere. Okay? So expected result, prediction, and estimate. Those are important terms here. Oh, I missed a slide. So I'm missing a slide here, so you'll have to bear with me a little bit. So in terms of modeling climate then, what we're dealing with are not numerical weather prediction models, but we're dealing with global climate models. And the idea is that global climate models take in different types of information. Okay? They're taking in boundary conditions and just the initial state still of the atmosphere, but then you have to make certain assumptions about what the climate forcing is going to be into the future. Projecting into the future using global climate models takes a lot of assumption, okay? So we're all probably familiar with the IPCC projections for future climate, and this is what they use, what are called representative concentration pathways, or RCPs. Another way to look at it, I think is more tangible for this audience, and myself included, are to look at the RCP carbon dioxide equivalents. So this is the possible, making assumptions about what our carbon dioxide is going to be like in the future. And we can see here, we're presently around the 400 parts per million. Obviously, this is probably closer to a business as usual, where we get up over 1,100 parts per million here. So, and these are an array of scenarios. So, strict, probably aggressive climate change policy. And you still see the inertia that Ellen was talking about in terms of carbon dioxide that's already in the air and how much we're already committed to. So, the important part here is that this is based on assumptions of what the climate is going to be, how it's going to respond. So assuming that these RCPs are reached, then the models show how will the temperature over land respond. So this graph shows the more business as usual versus kind of the aggressive policy. And you can still see even a very aggressive, I think impossible at this point to be this aggressive, you still get a commitment to change. And of course, as you go out in time, that cone spreads out even further, okay? So we're talking about ranges and assumptions of what's going to happen. And if so, then what happens spatially? We can see, I'm just showing the temperature on the top and precipitation changes here on the bottom. So you can see even the most aggressive climate change policy, we're still getting warming in the system. And this is, for me with a 5-year-old daughter, this is a scary thought. Now, kind of bringing these together, okay, so we're connecting weather and climate. We're talking about pushing the extremes, and you've heard that already today. So how changing climate changes weather. So if you imagine this curve right here was our old climate, okay, so just kind of this normalized curve here with the mean right here, this average in the middle. And we get, obviously, cooler climate here, cooler weather here, warmer weather here, very cold extreme, very warm extreme. But then we increase the mean of our temperature this way, okay? So now what are you doing? You're getting fewer of the cold weather events, but you still get them, right? But the ability to achieve hotter weather and even the more record hot weather is easily attainable. And so that's the link that's occurring here between climate change as we increase the mean in our temperature. And this is just temperature. There's a lot of other things that are occurring in the climate, but you increase the temperature, then your ability to hit those record extremes goes up. And that's very important in the link now in the debate of attributing weather variability to our climate change. So the takeaway messages then, weather and climate are obviously related, but climate is highly dependent on the temporal scale. Okay, so we're looking at long-term changes. And changing climate alters the associated weather patterns. Okay? Models that are used to predict the weather depend on the current observed state of the atmosphere. This is called an analysis, and they result in an expected future result, a prediction, that must be interpreted by the forecaster. Okay? And that's happening continuously, every hour, every day. Models used to project climate reflect an array of possible scenarios based on assumptions that are made related to the future climate forcing. The hot topic is CO2. So I'm challenging you to think about what are the missing assumptions in those climate scenarios, okay? And is the future climate captured by our current understanding? Because we're not, the political arena will be changing, the economic arena will be changing, perhaps greener energy could mitigate some of those effects, but this is really just to leave you with thoughts about the assumptions that are being made about the projections, and could it be worse than what we're seeing from the IPCC currently? Okay. Thank you.